Thank you very much for coming, everyone. My name is Chris Horner. I'm an Android developer working on the design systems team at Cash App. And today I want to talk about building creative and weird UIs with Compose. And to do that, we are going to build something together, piece by piece. We're going to analyze a complicated UI and put it together. But before I start doing that, I kind of want to give some context as to why I'm giving this talk in the first place. So here are some screenshots from apps that I use on my phone all the time. And something that sticks out to me is actually just how consistent UIs, especially in mobile, have become. Like, let's look at these two in particular here, Spotify and Pocket Casts, two very different developers, but everything down to the color of the now playing section is the same between these. And honestly, like, my brain really likes this. Like, these days when I go to use an application, I don't have to think about how to use it. I just pick it up and it does the thing that I want it to do, and it's great. But it does kind of remind me of something that a designer once said to me when they were talking about their job. And they said, I arrange rectangles. And they followed it up with, sometimes if I want to get fancy, I round the corners. And they were being tongue-in-cheek about this, but I think, like all good jokes, there is actually an element of truth to this. And if we go back and look at all of these UIs, I can see a lot of rectangles. And in fact, we can see that the designers of these applications decided to get fancy, and they rounded the corners. But as developers, we also know that the rectangles don't stop here. It's actually rectangles all the way down. We build our user interfaces out of rectangles. And you know, that's fine. Like, our UI frameworks are built around rectangles. This makes sense. When we think about the device that we start with, it itself is a rectangle. And then our jobs as developers is often to come up with creative and novel ways to arrange and nest rectangles. That's what we do. And this does lead itself and lend itself very well to the concept of, like, what I'm going to call flat design. And we'll use the Fitbit app here as kind of like a really good example of flat design. Flat design has a lot of advantages. You can think about how easy it would be for a designer to put this together. If you know anything about Figma, you can kind of whip this up pretty quickly. For developers, it's easy for us to build. There's no custom assets here that a designer really needs to export. We can just take this and write the code that we need. As a user, there's not too much going on here. It's easy for me to read. We can also think how easy this would be to stretch and scale to different screen sizes. Because there aren't any custom textures anywhere, everything can kind of scale and grow responsively. Pretty nice. Lastly, dark mode should really just be a palette swap away here. Except I do want to throw a little bit of shade at Fitbit specifically because they do not support dark mode, and I don't know why. But there is something else about this UI that I want to talk about. And that's that it's kind of boring, right? Boring is good a lot of the time. There are certain things that I want to be boring. Like when I make a phone call or contact customer support, navigate somewhere, send an email. I don't want some designer to reinvent the wheel, make this some new amazing experience. I just want to get the job done. But I am wondering if maybe we've gone too far and all of our UIs now are kind of boring. And I don't think it was always this way. I actually want to go back in time and have a look at what UIs used to be like. So we're going to go back in time with the magic of Keynote. Is everyone ready? Whoa! The year is 2009. How good is that? Love 2009. In 2009, iOS looked something like this. We were writing notes on actual notepads. We were picking up news from an actual newsstand. If you wanted to record audio, you spoke into an actual microphone, complete with decibel meter. Pretty sick. In 2009, HTC, may they rest in peace, released the HTC Hero. I absolutely loved this phone, and also the Sense UI skin that was running on top of it, this lovely like Web 2.0 glossiness to everything. Super cool. And I know it maybe looks a little bit tacky in today's day and age, but when you look at the weather widget, the way the droplets hit the screen, and then a windscreen wiper like comes in to brush them off, yeah, weird, but there's whimsy to this. Someone cared, someone got creative, and we've lost some of that. In 2009, we saw the decline of one of the all-time greats, Winamp. Winamp, if you're not familiar with it, was a desktop music player that let you play your local music files. It's pretty cool. What people loved about Winamp was, yeah, it had this default skin, this kind of futuristic cassette player, but you could also skin it and make it look like anything you wanted. It could become yours. And that meant that people made all kinds of skins for Winamp. Were all of them good? Absolutely not. But there's some genuine creativity here. I think that's great. If you also think that's great, all of these skins have actually been preserved in a Winamp skin museum that you can visit here. It's cool. But it's not old versions of mobile operating systems or music players I want to talk about today. I actually want to talk about video games. I think video games have some of the coolest UIs around, and they've never really stopped innovating, and that's because their main purpose is to entertain, not really get something done. And so they've really pushed the boundaries. And there's one video game in particular I want to talk about today. And this was actually released all the way back in 2016 in Japan. This is a game called Persona 5. It's had a lot written about its UI, all of the kind of amazing transitions it has. Let's check it out. What does it look like in-game? This is a turn-based game. That means the player has time to look through a fairly complicated UI here, all of the options that are available to them. And then as they start navigating through it, all of these wonderful transitions happen. Things burst out of all the different menu items. The other part here I really love is the way the options kind of explode out from the character here, really blurring the lines between the 3D game world and the 2D UI. There's an obvious influence of manga here, being a Japanese game, but maybe less obvious is the influence of 70s British punk rock magazines. And rebellion is a really big theme of the game, and so I can't think of a better source of inspiration to draw from. But the fact that someone can look at this and say, yeah, I can build a UI out of that, is really cool. Like, look at the main menu, the way the character holds up his hand to the camera as if to say, like, don't look at me, paparazzi. At this point, though, you might be wondering, what has this got to do with Compose UI and Kotlin? Why are we here? Well, there is a more familiar scene in the game, and that's when the characters are in class, and they want to talk to each other. And to do that, they pull out their phones and use a messaging application. But this messaging app was unlike any messaging app I had ever seen. Even the messaging app in this game was full of interesting transitions, cool stuff going on. And that made me wonder, could we build this in Compose UI? Is this actually possible? And so that's what we're going to do today. We're going to build this UI together. It's a little bit weird, though, when you look at it. It immediately breaks our rules. This basic shape here, not a rectangle, even if we tilt it just to the side. All of our portraits here, not rectangles. Same deal for the avatars, certainly not. There's this weird line that's kind of running between all the different avatars, connecting them together. How are we going to draw that? And then have a look at these animations that occur as new items come in. Maybe kind of hard to see that fast. Let's watch it again in slow motion. So many little bits and pieces we're going to have to animate. So we've got a lot of work ahead of us, so let's get started. We'll start with something easy, just the background. Let's pretend we get this as a spec from our designer, maybe a scene that has less going on, a bit more easy to reason about. I'm going to start by declaring, yep, this is the Persona red color. We're going to use this all throughout our app. And I'm going to set that as the background color of a box. It's going to be the root of our whole UI. It does have this weird splatter effect around the corners. I think in order to get that drawn, I'm just going to put an image inside the box. Done. While I'm here placing images, may as well put the IM logo up in the top left as well. So pushing this to an emulator, this is what we get. Looks something like this. Not bad, but still fairly simple. Let's move on to something more complicated. How are we going to draw each one of these text boxes? So the text box, when you look at it, is sort of an interesting shape, this weird like trapezoidal thing. And that actually presents a few challenges for us. We can't really just get a designer to export an image for us to use, because if we have a smaller amount of text like this, if we were to just scale it down to fit, it starts to look a bit weird on the sides here, like this. Not quite what we want. This got me thinking, how am I going to render this dynamically? Well, in the past, I've used 9patches, a very, very old tool from back in the old Android days. But Roman Guy has actually done the work to make this now work for Compose UI and vectors. Very great. If you're not familiar with it, 9patches basically let you declare parts of an image where you say these can stretch, and then other parts, like the corners here, that you want to remain constant. Cool, but it's actually not going to work for us. And one of the reasons why, if we load in a slightly longer message, let's draw a blue bounding box over our text composables to get an idea of how they kind of relate to their background. If we extend that blue border all the way to the right-hand side, you can see for longer messages, that angle on the side, it changes. And 9patches really only work when you have a straight line. Damn, not a problem, like, not something we can use. What is constant, however, is the amount of distance between the corners of our text composable and the actual background box itself. That should actually have everything we need in order to render. Compose UI has this really fun function called generic shape. And it does let you build up a shape, but what's special about it is how it gives you the size parameter to work with. Size is fantastic for us because it means we don't need to know how big this thing is going to be ahead of time. We just get to know how big it is when it's time to render. The way this API works is we start with a call to move to. So you can think of this a little bit like you've got a pencil and you're moving it to a particular coordinate on a sheet of paper, but you haven't put the pencil down yet. Next we call line to. So line to is like you've actually now put the pencil down on paper and you're drawing a line to another coordinate. And here you can see where that size parameter is coming into play. We don't care how long our text composable happen to be, we're just saying we're going to draw all the way to the end and coordinate 0 for the y coordinate. Another line to call, this time you can see we're using both width and height. We're going to draw down to that bottom right-hand corner. Line to, and then finally close. So close says, yes, we're done. This is the shape that we want to use. Of course, generic shape, it's a fairly rendering-specific primitive inside of Compose UI. And what that means is we've declared all of these points, but they're all in pixels. For designs, though, you typically want to do this in DP because we don't know the density of the device that we happen to be running on. Thankfully, fairly easy. We can just make this an extension function on top of the density type, and then we can say, yes, all of these original coordinates were in DP, and then we'll convert them into pixels. We can repeat this process for the next part of our text blocks, and you can see how we start to layer up all of these different shapes. And at this point, you might be saying, well, Chris, that's great, but does that mean I have to like talk to my designer, get all these coordinates and put it together? That sounds tedious. And yeah, it kind of is. Thankfully, there is a Figma plugin you can use called Shape Composer Figma. And what that will do is, for some given path data in Figma, will actually let you export compose code. It won't quite give you the same dynamic sizing with the size parameter, but it gets you very close that you can then kind of just tweak the values in the end. The actual text composable itself, nothing terribly interesting about this, I think, except for maybe the custom font. It's cool. What is more interesting is how we go to actually draw the components of the text box behind it. So we're going to use draw behind. Draw behind is neat because it's going to draw behind, but it itself is also an extension function on top of that density type. And that means that we can just instantiate our two shapes, the outer box and the inner box. You would then think there must be a function called drawShape, right, that takes these different shapes we've made, and we'll draw them in black and white. Unfortunately, this API doesn't exist. Instead, there is one called drawOutline. Thankfully, it's very easy to take a shape and turn it into an outline. Lastly, we'll add some padding so that it roughly matches the game, and then we'll push this to an emulator just to see how it looks. Not bad. We're getting close. But what's fun about this is now we're actually running in Compose UI. And that means we can support things that the original developers of the game never really thought about. Things like accessible font scaling, we can crank that up, and our background is going to scale and adapt to it. All right, the avatar. How are we going to draw these? So the avatar, when you look at it, it's actually pretty similar to the text box, right? We've got a whole bunch of shapes, all in different colors that we're drawing one on top of the other, with the added problem of this image that needs to kind of draw both on top and inside of this shape at the same time. It's maybe more obvious if I reduce the opacity here just a little bit, and you can see that bottom edge. We're going to need to clip that somehow. Well, let's start working on this. We've got our avatar and our text box. I'm probably going to want to put both of them inside of a row like this, and we'll push that to an emulator. What does it look like? Not bad. The image I'm going to place inside of a box, and here we'll do exactly what we're doing for the text box again, where we're saying draw behind, here are all of my different shapes. Great. To actually get this masking to happen, let's look at the kind of shape that we want to use. And so for a second here, I'm just going to define this as another outline and use a lovely magenta color here for debug purposes. It gives you an idea of how we want to clip this shape. What's neat about the outline API is it's not just for drawing, it's also for clipping. So we can pass this to this clip modifier, and so long as it's the last one in the chain, that means that everything inside of the box is going to be clipped to this, but all of the other calls prior to clip won't be clipped. So we get this exact effect that we want. So far, I've kind of been cheating a little bit, though. We've drawn the avatar and the text box, but we've ignored the stem that connects them, and our layout doesn't really match. One of the reasons I've ignored this is some of the complexities it introduces when it comes time to animate. And I want you to pay close attention to the left-hand edge here of the text box. You can see as it grows in, the white part of the text box stays fairly stable, and that's annoying. So if we're laying these components out together, you might think, well, the stem could just be a child that sits in between the avatar and the text box in a row. But we really want the stem and the text box to be one composable child. And the reason for that is we have to talk about how this thing renders and what the ordering is. We have to start with the white part of the stem, then go to the white part of the text box, then the black part of the stem, and then finally the black part of the text box. And this order matters a lot. And I'll show you why if we do any other combination here. And it's maybe a little bit more obvious if I scale them down to roughly match the start of the animation. You can see the white lines don't really line up and give us the same nice effect that the game had as it was loading the message in. So really, we need all of the different components of this text box to be drawn in a specific order. It has to be the one composable. Okay, if it's one composable then, it's sitting off to the side of the avatar. We want it to overlap a little bit. Does that mean that we could just use an offset modifier, pass in a negative value, have it overlap a little bit? One of the problems we run into is that's going to leave us with this little gap on the right-hand side. Fine for a short message like this, but if we load in a longer message, you can see we really want to use all of the available horizontal space here. We also have some other complicated layout rules. When the message is short, the message anchors itself to the bottom of the avatar. But as messages get longer, it anchors itself to the top of the avatar. We've got all of these custom rules here that we're starting to talk about. It's maybe time to use a custom layout. So a quick refresher on custom layouts, if you're not familiar with them. We've got two lambdas that we care about here. One for content that lets you say, yeah, here's all the composables that I want to render. And then this other one where we actually do the layout work where we get measurables and constraints. The way this typically works is you iterate over each of your measurables to get placeables, and then for a given width and height, you place each of your placeables. That's sort of the process taken by a lot of very generic layouts in Compose UI. But we're not building a generic layout. We're building this layout, exactly. And that means we get to cheat and be specific. We know that we are only ever going to have the avatar and the text box as children. What's neat about that is we can use Kotlin's destructured declarations on all of our measurables. I always forget that I can do this with collections. I do it with data classes all the time, but collections let you do it too. And here we know we've only ever got these two types. The avatar is simple. It just gets to be as big as it wants to be, no custom logic. The text is slightly more complicated because we're going to have to do a little bit of maths. So here we want to take the total width of the row that we're displaying in, and then actually subtract how big the avatar was, and then add in a little bit of overlap padding here. So I'm going to say that that's roughly 18 dp. Once we've got that in place, we can create some new constraints and measure our text to get a text placeable. We'll calculate some width and height. You don't need to pay too much attention to this. It's just us looking at which one needs to be bigger. But once we've got the width and height, we can start putting things down. So the avatar is always going to be in position 0, 0, nice and simple. Text placeable is slightly more complicated because, again, we're looking at which one is going to be bigger. But I think what's neat about this is that in roughly like 14 lines of code, we've got a layout that does this very specific thing that we want. And I think it's nice and powerful. So it does both of these different layouts. We'll push this to an emulator, and we'll look at all of it in a list, starting to look like the video game. Worth noting, I'm using a LazyColumn here. The reason I want to use a LazyColumn is I don't know how many messages we're going to have. It could be lots. We need to put it in some kind of container that is going to recycle all of these items. But if it's in a LazyColumn, how are we going to render the line between all of those different elements? This was maybe the hardest part of the application to replicate. So let's start by analyzing the line's behavior here. You can see it sort of anchors itself to the very center of the first item in the list. And then it zigzags left and right by a certain random amount every time. It's not constant. And then it finally anchors itself to the very last item in the list. And then as new items are added, it actually then jumps to what I'll call a final position on the left or right-hand side, and then animates down to connect itself to the newly added item. To go any further, we're going to have to talk about how we model the data. We'll start by declaring a sender. This is a video game. There's a finite number of characters. We'll declare it as an enum. And we'll wrap all of that in a message type. So the message is basically the sender plus the text that they happen to send for this particular message. Next, we're going to need some line coordinates. And by line coordinates, I'm talking about these 2 points here, on our line. And we're going to store those in Compose UI's offset type. And that's very important. We'll get back to why in a second. You could think that maybe we'd store this as a single point and maybe a width property, but when it comes time to draw, it's going to be easier if we have 2 different points. We can put all of this together in an entry type. So that has the message we were talking about and those line coordinates. So you can think of the entry as being like the total collection of everything we need when it comes time to render. Where are we going to store all of these different entries? You first thought might be viewModel. ViewModel is often where people go to store data for a screen. But I would actually argue that UI state is a better place for this. And by UI state, I'm talking about things like remember scroll state, remember pager state. If you've ever used any of the Compose UI primitives, you're familiar with these. We can also write our own. ViewModel is really good for the kind of like nuts and bolts data, the current list of messages. But the UI state is going to have all of those entries. It's got pixel coordinates in it. The ViewModel has no business knowing about that. It means we can also store things like item animation progress that we'll get to in a second. So if you want to think of the total flow of data throughout our application, we're going from ViewModel to UI state, and then finally into the LazyColumn to let it draw. How do we make this state? We'll call it a transcript state, and we'll declare remember transcript state. The only thing really worth paying attention to here is how we're keying it off of density. So we're doing a lot of pixel calculations. If our density happens to change, maybe we're a foldable, whatever it is, we want to throw all of this information out and start again. Transcript state itself, we're going to declare as this stable type with a single public property of entries that's driven by a Compose UI state type. And that's just us pinky swearing to the Compose compiler to say, whenever this value changes, we're going to let you know. So that means as we start emitting 1 message, 2 messages, 3 messages, it's going to recompose. How do we calculate the line coordinates for each entry, though? Well, if we're centering to this first item, there's nothing terribly interesting here. We just take half the width of the line, half the width of the avatar, and then to get the other coordinate, we just plus on the width. And then the y coordinate is just halfway up the height of the avatar. We'll store all of this inside of some line coordinates. Great. If we were to draw this from, say, the previous message to this one, looks something like this. What if we want to go left and right? Well, we know that we always want to go left, then right, then left, then right. We can just look at the index of the current message and say, is it divisible by 2? Yes, no, we'll go one way or the other. And then we need to multiply that by some random offset. Remember, it's not the same every time. Fine. We can add that offset back to our line coordinates, and then we're shifted one way or the other. If we start to piece all of these together, and then render it black, and add a drop shadow, we're starting to look like the video game. But I said we were doing all of this inside of a LazyColumn. LazyColumn has its own state that it already uses. And then we're adding our own transcript state here to get all of these entries, and we're piping it into the LazyColumn. My first thought here was, well, that should give us everything we need, this list state and the entries. We could declare a new background line composable that just sits behind the LazyColumn and renders the line. The idea of how this would work would be to use this particular property of LazyListState here, this offset type on top of LazyListItemInfo. And it's got this fun comment on it that says, the main axis offset of the item in pixels, it is relative to the start of the LazyList container. Which sounds perfect, right? If we look at this yellow avatar entry here, it should be this coordinate here. And then as we scroll, we should receive updates as to where it is. So my first attempt at this was like, great, I'll just get a canvas and I'll start getting that new point as it updates over time and rendering this polygon. Don't pay too much attention to the code, because if we push it to an emulator and have a look at it, it's fine when it's static. But as we start to scroll, you can see it's not giving us those updates as quickly as we wanted. Doesn't look great. And I think actually maybe even more annoying to me, it's not synchronized with Android's overscroll behavior, so it looks really weird. Back to the drawing board. The reason I want to talk about that, though, is when you're doing something this weird, sometimes you're going to have a couple of goes at getting it right. So the big problem we have with this layout is that the total height of each message is different. We don't know what it's going to be. What's constant, however, is what I'm going to refer to as the overlap height. So we know that the line is going to draw from one avatar, and it's going to be at least as tall as the individual message itself. We could actually draw into the next message. If we did this as the background of one of these row items, because we know we place that avatar at 0, 0, we know that we can always kind of find the exact spot we need to connect to. And if we start drawing that background for each one of our items, you can see how we start piecing together the line. How would we build that? Well, let's declare a new modifier. We'll call it drawConnectingLine. It takes in 2 entries, the current one, and then what we're connecting to. We'll make that nullable because maybe we're the last item in the list. And then we're going to use drawWithCache. drawWithCache I really like because it lets us do a bunch of calculations up front, and then so long as the size of the component doesn't change, we get to hold on to all of those calculations. Particularly of note, this path object. I want to reuse this as often as possible. Next, in onDrawBehind, this code should be starting to look very familiar to everyone now in this presentation. We're drawing a bunch of lines. The only thing that's really different here is how we're calling rewind at the start, because we want to reuse this path object every time we go to draw, not allocate a new one. To get the drop shadow to render, slightly more complicated. It is the same shape. We can reuse the same path data, but at this point we need to use we need to get access to the paint as the framework paint. And so that means your code is going to be slightly different between Android, or if you're targeting desktop, or iOS, you're going to need the skier mask filter. Slightly more complicated, but it means, sure, you write this twice, and then you've got a drop shadow that works on different platforms. Let's push this to an emulator. What does it look like? Much better. It's in sync. It's because it's the background of each item. The overscroll effect works the way we want. Great. But now we need to animate a bunch of things, the things that actually make this like come to life. How do we do that? Well, we said we had this entry type, and it has everything we need when it comes time to draw. So let's start using it for more things. We're going to add a line progress property here. So by line progress, this is going to be a floating point value that animates from 0 to 1 over time. So if it were, say, 0.5, that would mean that the line would be halfway connected between these two items. The avatar background and foreground, unfortunately, they animate in at slightly different times, so we need two different properties for each of those. For the message itself, its horizontal and vertical scale are different, so two more properties, and then also the alpha of the text. But this should be everything we need in order to animate an individual message. To build this, I'm going to use Compose UI's animatable type. I like this type for two reasons. The first one is it lets us specify an initial value. So the avatar background scale actually starts at 60%. They really cheat here. And then the other reason I like it is it's got this coroutine-based API. So we get to call a suspend function that says animate to 1 now over 300 milliseconds. Of course, the type of animatable is slightly annoying. We don't really want to expose this to our UI code. We don't want to let them know how the animation sausage was made. We just want to give them a value that changes over time. And thankfully, we can do that. There is this asState function call on top of animatable. So we get to hide that implementation detail. Where this coroutine-based API really starts to pay dividends is when you've got something more complicated here. So like the avatar foreground scale, for example, it actually starts at 0. We don't want to show it at all. And then after 160 milliseconds, we then want to immediately jump to 80% completed, and then finally, over the last 150 milliseconds, animate to 1. Our consuming code then actually gets to be kind of simple. For this background component here, we just say the scale is whatever the animated value is. The foreground, however, slightly more complicated, and that's because we're not scaling from the center of the image. We're actually scaling up from the bottom here. And in order to get that effect right, we're going to need to use graphics layer. Graphics layer is very useful because it lets you specify a pivot fraction. So we say that the x-coordinate is in the middle, and then the y-coordinate is actually 115% below where this image is. And that lets us get that nice kind of like scale up effect. How do we animate the line? Well, we said before that we had a bunch of points that we were using between all of our different entries, bottom left, bottom right, top right. As this item animates, we need to find a point in 2D space for each of these lines and kind of draw that over time. To calculate that point in space, there's actually this fun function in Compose UI called Lurp. Lurp, if you've never heard of it, it means linearly interpolate. And there's a bunch of these values. You can actually linearly interpolate between two integer values. So say you passed in 0 and 10, and you pass in 0.5, it will give you 5. But the Lurp function we care about is one that takes in that offset type we were using before. So it lets us calculate a point in 2D space. You might be saying, well, that's cool, but does that mean that we're allocating new offset objects every single frame as we animate this? And normally, you'd be right, but actually offset is a Kotlin value type. And what that means is when you're writing your code, you get to use this thing as if it were a class. It had functions, you're invoking them. But then at runtime, it's taking those two 32-bit floating point values for x and y, and it's packing them into a single 64-bit long. And so the cost at runtime is just some bit shifting operations in order to get those values out. You're not allocating a new object. Pretty cool. Lastly, we've got this typing indicator, these dots that move. This is even simpler again, and you just get to have fun with coroutines. You can say, I'm going to wait a little bit and then make this thing visible, wait a little bit, make this thing visible. It's cool. If we piece all of this together, it looks like this. Maybe kind of hard to appreciate at this speed. We did all of this work. Let's slow it down again. How did we do? So the avatar foreground animates in at the right time. Our line connects nice and smoothly. Jumps to the left-hand side as there's a new message coming in. Great. There's one other fun piece of this, though, that we didn't talk about, and that's particles. We had these snowflakes floating in the background. Things change depending on the season. So we're starting to get to the end of this presentation, so I'll go through this a little bit faster. The way this is going to work is I'm going to declare a new composable called background particles. That takes in whatever the current season is, and then we're going to draw this with a canvas. Drawing something like this to a canvas that changes over time is actually a little bit like writing code for a video game. If you've ever done that before, you've got this basic loop of input, update, render. We need to update a simulation and then render it every frame. So we're going to get that current time, how we're moving through time, from this remember time millis composable. The way we've set this up is it's basically using this with frame millis that the framework gives us. So that's a suspend function that waits until the next frame renders. And we can use that in order to calculate the delta time to drive our simulation. Particle state, the way this basic particle system works, is it has two different collections. The active particles, the ones that are actually on screen at the moment, and then a pool of available particles for us to draw from. The reason we want to do this is we're trying to minimize the number of allocations we're doing every single frame. Publicly, the things that we expose are all of those active particles for that canvas to render, and then this update function that takes in some time, and then whatever our world size happens to be. We start by looking at whatever the current time is, and if we pass some particular threshold, then we're going to spawn a particle. Basically, that just involves taking it from the pool and moving it to active. Next thing we're going to do is iterate through all of our active particles, but in reverse. The reason we're doing this in reverse is because the first thing we want to check is, have any of our particles gone outside of the world bounds? If they have, then we want to shift them out of the active collection and back into the pool, ready to be used when another one needs to be spawned. If it hasn't gone outside the world bounds, though, then that means we get to do some fun stuff. Given that delta time, we can start modifying the rotation and then the x and y coordinates. So to roughly match the video game here, I decided a sine function kind of gives us that nice like floating effect of particles. And if we actually push that to an emulator, we'll say it's spring now, we're rendering some nice cherry blossoms, you get this effect of things moving in the background. So I talked about a bunch of stuff today, and it's kind of difficult for me to summarize what the takeaways are here, but I think Compose UI is actually a really cool framework for doing very creative things. Like that generic shape type, giving you the size, is fun. The Kotlin value types like offset, there's a bunch more like DP size, all kinds of things that let you write very expressive code in the IDE, but then you're not paying that same penalty at runtime of allocating an object. Some UIs should absolutely be boring, but I think collectively, everyone here is maybe tired of all UIs being boring all the time. I want just a little bit of whimsy back in my UI. Maybe we've lost some of the magic with all of this consistency that we've been chasing. And lastly, it's that video games, I think, have left us in the dust when it comes to innovation. They never really stopped. And so we should look at them for inspiration. So while I was actually coming up with this talk, the developers of Persona 5 came out with a new video game, Metaphor Refantatio. Again, an absolutely like crazy UI, lots going on, and people were like, well, you've done it again. This UI is excellent. And that led the director of the game to say this hilarious quote of, yeah, making beautiful menus is actually really annoying. And like it is, right? You see all those different things that we had to do. It was rough. But I think it's worth it. So another game that recently came out, Expedition 33, you can see where's its inspiration on its sleeve here. This is made by a French studio, so people are talking about the previous game was a JRPG, and now this is a JRPG. Super great, though. Absolutely love that people were able to take this and run with it. If you want a more like curated collection of UIs to look through, this game UI database is an absolutely incredible resource. The maintainers have kind of like indexed everything, made it very searchable, cool to look through. Lastly, we talked a lot today. We built a lot of things together, but there was obviously a lot of lines of code I didn't get to put on all of these slides. And I don't want this talk to be a draw a rest of the owl kind of thing. So I'm about to link you to these slides and all of the code. But before I do that, I will say thank you. Don't forget to vote, all of that stuff. But with that, here are all of the slides. You can find them here if there was anything that was interesting to you. All of the code for this application is up here on GitHub. And then if you want to talk to me about it at any point in time, you can find me here on Blue Sky. But with that, I'll say thank you very much for coming.